All right, so any questions from homework? Yeah.
Could you do 35 on 3-2?
3.2?
Yes.
35. All right, so you get so the funny thing here is now that you know synthetic, don't think suddenly everything has to require synthetic. This is actually even before the synthetic section. So you shouldn't need it. What do you try when you have this many terms? Grouping. So then what comes out as the first group?
X squared.
Squared, good.
2x squared.
Cool, right? Not 2x, of course, right? Why do you think somebody would write that? Because I get that all the time. But they got that very recently. Why do you think somebody would think it was that? Because they see x squared and they see that x squared. They say, I took them all out, so there's nothing left. That's not true. You divided by x squared, so there's that 1 left, right? All right, cool. I think you all looked at me like I didn't know what the hell I was doing, so that's great. You should look like me like that. That should be a silly thing. Now, what do you do over here? Yeah, you have to take out a negative to make this become positive like that's supposed to be, right? And you have to take out a 9 because, well, 2 reasons. That's the only damn thing that'll come out. But also because 18x divided by 9 gives you 2x. Right? You know you want this second dude to be the same as this first dude or else you screwed up or it's not factorable like that. You with me? I always get somebody get something different here and somehow they do the next step. And I'm like, whoa. So what happens when you take a negative 9 out? Thank God you get the same damn thing you had over here. So then it's legal to do the next step, which is what? And I have people tell me this, and I think I already showed you this mistake. Right? And you can see why they would think this. They think, oh, there's 2 of them. No, there isn't. There's one of them that was distributed to both. Right? Yes, sir.
So when you pull up the negative, that doesn't change the negative sign that's already there?
You did. That was negative 18, now it's positive 2. That was positive 9, now it's negative 1. So it changed both the signs. Cool. And of course, I'm not done.
X minus 6 plus 3.
Yeah. And then you can find the zeros from there. Right? The zeros would be what?
3.
Yeah, 3, 0, negative 3, 0, 1 half, 0. I like it. Cool. So if I had a polynomial that had 5/7 as a factor, as a 0, what would the factor look like associated to that? Don't give me that. Give me I want a factor with no fractions in it. I want whole numbers, integers.
7x plus 5.
I like the 7x idea. 7x
Plus 35.
minus 5. I like it. Because then you would add 5, divide by 7. That's where the hell that would come from. Because where'd 1 half come from? Add 1, divide by 2. You guys with me? I love you guys. You have like less than 0 reaction. I'm not sure how you do that. Yeah, it's like a black hole of reaction. It sucks in all the reactions around you. That's a little scary. All right. Anything else from homework?
Could you do 40 on the same section?
Yeah, this one, I think we talked about something like this back when we were doing the review. Where'd it go? There it is. What gets in people's way is the powers, but all I care about is the fact that this first power is double this guy. So what the hell has that got to do with anything? Well, how do I factor this?
We could just use substitution.
You could. But I'm trying to show you don't need to. I mean, new sub's really, really powerful, really cool, but I want you to save it for when it really helps. You could use it here, and I don't want to get me wrong, but you shouldn't need to. Because the idea is just so simple, it doesn't require it yet. How do you factor this guy? What goes here and here? X and X, right? To make X squared. And thank God the middle term has an X in it, so that when I multiply, I get X, I get X's. So if this is X6, what's going to go here in the front? And thank God the middle term has freaking X cubes in it, so the middle dude's power has to be half this guy's power, because the first thing you do is cut this guy in half. So if I had X12, I better have X6. There, right? And then the numbers work the same way. The numbers will, what numbers work here? Yeah.
With
2 minuses. Minus 1 makes minus 2. And minus is plus. Is that cool? Are you done?
No, you have to finish.
No, you're not. All right, now each of these is a difference of cubes. One of our favorite ones. The nice thing is once you get one, the other one's the same. Yeah, that's the reason I like that. What do you think about that? Little dude, big dude, right?
X minus 1.
It's going to be that thing basically squared. Is that cool? Because each one of them gets the same stuff. Bless you. So what goes on the little dude?
X minus 1.
Good. Got it. 1, 1, 1. So X minus 1. So these two go
X squared.
X squared. That's on the end. Middle one's got to be positive so it can cancel stuff out. 1x. Right, that's cubes. Everybody forgets the poor little cubes, dude. It's really not that bad. 1 of each, 2 of each, product in the middle. That's the closest to a song I'll ever get. I'm a poet and didn't realize it. That's an old joke? Alright, sorry. But a poet and didn't know it? You guys know that saying? So you just make it extra. I'm a poet, didn't realize it. Is that cool for that one? Alright.
How would you set it up if it was like x to the 7 minus 2x cubed? Would you just like draw?
You can't do it.
You can't do it?
Yeah, you can't do it this way. You might be able to do synthetic division. Synthetic division might be able to handle it and just put a bunch of zeros in and try out some factors from the end. You with me?
Yeah.
But traditional methods of factoring would completely die. That's why once we learn synthetic, we're able to do all of this other stuff. Okay. Anything else from homework? I'd say you should be, well, you should have 3 done, to be completely honest. Yeah.
Is it okay if I ask about 2.7?
Yeah. Anything up to this next test coming up?
Yeah, 2.7, number 36.
Oh, this just ends up looking disgusting. How do you verify F and G are inverses?
Just see if one equals.
I'll tell you what you don't do, is you don't find the inverse by switching x and y. No, that's crap. Right? It's sort of like when I teach my Math 88 class and I say to them, show me that this is a solution to this equation, so they solve the equation. No. You plug the damn thing in. So that's really the same thing here. They show that they're inverses. If you do plug one in to the other one,
Plug gx into the inverse of x.
no, just plug gx into f. And if they are inverses, what should they do?
Undo each other.
Equal x.
It should equal x. So now you get to see that idea concretely. Right? You're like, yay! Yeah.
So would it be incorrect if you like found the inverse of f of x and?
Yes, it would. Don't do that.
All right.
Because then you can say, oh, it's g, which I don't want you to get me wrong. That's fine. Then you find the inverse is great. But how do you verify that's the real inverse? You plug it back into the original. So that's what we're doing. We're verifying our solution. So if you just resolve it, you might have made the same damn mistake. You want to verify it. You want to do something new to it to show that it does work.
All right, yeah, because I did that for.
All right, go back and redo all of them. Oh, shit. Which one was this one again? 40?
36.
36. Oh, yeah. tell me f of x is x minus 5 over 3x plus 4. G of x is 5 plus 4x over 1 minus 3x. And this is where people just kind of give up on this poor little dude. This is the kind of math you need to be able to just do. You need to be able to just attack this thing. Appreciate the math when it's at the point where you just need stamina to get through, not this higher level of understanding. This is not a high level of understanding yet. This is just plug away at it. So if you plug this into here, what would f of 5 plus 4x over 1 minus 3, what would that look like? Where does that go? This whole thing
Into the x box.
goes wherever there's an x. And that's when people go, no thank you. And they leave it blank. Or they leave number 36 out entirely. Like, please, Mr. Waller, don't notice. I actually had a teacher that would not notice that. I did that a couple times, but I will notice it. Right? Just leave it out and say, oh yeah, I forgot I assigned that. So if I plug this whole thing in, it'll look like 5 plus 4x over 1 minus 3x. So that's there, minus 5 over 3 times 5 plus 4x over 1 minus 3x plus 4. Now somehow that equals x. And you just have to start attacking it. I mean, what method? There's a couple different ways you could approach this.
Factor out the bottom and flip them.
How do you factor out the
Not
bottom?
factor it out, but expand it and flip them.
So be a little more precise.
Okay, so expand out that bottom that's in the parentheses, and then multiply it by its inverse. But then multiply the whole.
You can't do that yet. You'd have to actually, if you want to go that route, you have to combine these first. So you need LCD, right? So you can do the same thing on the top. You can get the LCD, combine them, and then it's fraction divided by fraction, which is fraction times reciprocal of the other fraction, right? That's nice. Personally, I like to do it by just multiplying top and bottom by the LCD. And of course the LCD is, because there's only one frickin' fraction inside that fraction, right? It's 1 minus 3x. There's only one denominator in there. So if you multiply top and bottom by 1 minus 3x, I've given away too much. That's far enough for me. Right? Just be careful. It distributes and kills that dude, distributes, and that guy picks him up, and the same thing happens on the bottom. The beautiful thing is you won't have a fraction inside of a fraction anymore. You very directly kill the inside fraction. If you don't like killing anything, you can do it the other way. Get LCDs, combine the top and the bottom, multiply by the reciprocal. Something's still going to die. So this is the way it is. That's nature. Okay. Anything else? Yeah.
I was wondering when you're going to give out a study guide for the exam.
So on Wednesday, I'll have the practice test for the next test. The next test is a week from this Wednesday. So always a week before the test, I give the practice test. The following class, this next Monday, I'll have the answer key.
Okay.
So next Monday will be review day. We won't do anything new. Yeah. Okay. Is that cool? Whoever asked that?
Yeah.
Yes. Okay. All right. So let's get back. Last time we finished up section 3.5, but I want to say a couple things here. Something to introduce in the next section is very often you'll see a complex number given it's kind of like the variable that's normally used for a complex number is the variable z. I can hear one of my early math teachers, z. You do z here, z there. And then the symbol for conjugate, what would this guy's conjugate be?
A minus B.
And that symbol is very often just z with a bar. So can anybody tell me anything about that? Without doing any work, can you tell me something that will always be true about that?
It's going to be a difference in squares.
In a way, I like it. It's related to a difference of squares, but the answer will always come out to be non-imaginary, otherwise known as real.
Real, yeah.
So this will always be real. Which is neat. And you can see if you did the multiplication, the BI, the I stuff would only be in the middle terms, and the middle terms cancel. Because at the end you'll get negative BI squared, but I squared is negative 1. The most important power of I to know. Okay. Alright, so that kind of comes up in a few places. So if you see that in the homework, that's all they mean, the A plus BI or its conjugate. Okay, cool. And then we have this here. Oh, there it is. Okay. Jump through this. Here we go. So if you have a polynomial, and a polynomial in general, let's see what symbols they use. Now, I don't know if you guys have ever seen it written like this before. Oh joy. Whenever you try to write something in general form, in some kind of way that will capture all possibilities, it will end up looking more complicated than it really is. So all this is showing you is that that's the coefficient that goes with the degree n term. So that's why we call it a sub n. Right? Where else have we seen these sub things before? Sequences. Good. Not all of us have seen it yet. In fact, that's chapter 11 in this book. So if you haven't done sequences before, you might not have seen them. But one place you guys have all definitely seen it.
Matrices and determinants.
Matrices, I love it. We officially haven't done matrices yet. You guys are neat. You know all this stuff in the future, but we haven't done it officially. Some of you guys in Math 110 have probably done some matrices stuff, right? And they normally have like A, I, J to denote the ith and jth, the ith column and the jth row and all that kind of stuff, but I'm not going that far. What about this? M equals slope. On the bottom, I like it. So all a subscript means is a specific number for that idea, right? When I see a subscript on something, it's a specific number. Normally in physics you would see like HO, which means the initial height, and then you drop something. Whee, right? So here, when I see that subscript, that just means the nth coefficient. That's a number. It could be, so an example, of course, is 7x to the 48th power plus 6x to the cube minus 2. Yay. So a whole bunch of these A's are zeros because I'm missing a bunch of these poor little dudes, right? But that's all right. They could be whatever number they want to be. All right, how are we doing so far? Is that okay? We know polynomials, so don't let this freak you out if you see this anywhere. This, all it's trying to do is capture this idea completely in general. Okay? So a couple little building block things there. So here's the big guy. I think I've already said this. So if I have a polynomial, this polynomial is degree what? Yeah, degree n. Right? This has degree n. So how many zeros must it have? So for example, if I had, how many zeros could it have is what I should say. So if I had x squared minus 4, what does that look like? It's a parabola that's down 4, right?
At least 2 zeros.
Yeah, see, it's got 2 zeros, right? So you're thinking about turning points. One turning point, so then it can have 1 0 and then one more 0. That's why it has one less turning point. If you had another turning point, oh shit, I get another 0. Oops, too many. So this has got to have n zeros. Now some of those might repeat. Right? So you could have, for example, you could have x minus 1 to the 7th power. What's the 0 of that? 1. Right? The x-intercept is also called the 0, also called the root. So it's only got, like, we'd say it only has 1 0, but math would say, no, it's got 7. They all happen to be 1. Right? So it's that multiplicity idea. You guys remember that word? It's not just a weird movie with Michael Keaton. You guys have never seen that? If you like Michael Keaton, go look it up. Netflix, something. So this has got a root of 1. Multiplicity 7. Okay. Cool. So at some point, I think I said basically that. I just want to make it a little more formal. Of course, some of those roots could be complex. Some of them could be real. Some of them could be repeated. But if I have a degree 11 polynomial, I must have 11 roots. I don't know what the hell they are, what they're made of, are they real, imaginary, I don't know. But I know there's 11 of them. So then we get to this point here. Let's do a problem out here. I think I told you last time, section 3.6 is basically section 3.4 with complex numbers thrown in. All right, so 3.4 was all about finding the zeros. 3.6 just says, oh yeah, you can find complex zeros also. So let me give you a basic example. What you got? Let's see. I like it. Well, fight the urge to combine the middle terms. I know it's set up kind of nicely for us. How do I factor this? Give it away to get going. So what happens when you factor this? What do you get? Good. Don't forget that little plus 1. And of course, you do the next step because those two are the same. So what comes out? Yeah, those two are the same. They come out. And what's left? All right, now in the previous math class we would stop there. Now we realize that's silly. Let's keep going. I officially cannot factor a sum of squares over the real numbers, but I can sure as all hell factor them over complex numbers. So I want this to be x plus 1, x minus 1, but that would always give me negative 1 as a product. So of course, what do I use instead? I. So knowing that, how do you factor this one? I love it. You guys cool so far? Yes? Alright, just to freak you out a little bit, which is nothing new, I guess. That's all I seem to do. What does that mean I should be able to do? What are the zeros then? I factored this polynomial. What are the zeros? Yeah, plus or minus I. Plus or minus 2I. I love it.
And plus or minus 4 and plus or minus 1.
No. What's the degree of the polynomial? Let me give you a couple reasons why not. It's a 4th degree polynomial, so it should have 4 answers, 4 zeros. It does. And you got those answers from here, but I haven't broken it down all the way yet. Yeah. Cool. Alright, so this is only the book that he's showing you. I just want to show it to you just because. What does it mean I should be able to do with I in relation to this thing? What should I do with this thing? That sounds weird. You guys said, I have a few ideas for you, Jack, but you can do that. But I should be able to synthetically divide using I. If you really want to, Jeff, go ahead. Screw that shit. You guys do it right now. Go ahead. And be careful. Go ahead and make this what it should be. It's really this. I just kind of did one step to make it easier to look at. Right? That's actually 5x squared. So what do you not want to forget?
The zeros.
The zeros. Let me help you out a little bit. There you go. You guys have fun. This is nowhere near as ugly as this kind of problem could be. It doesn't make me feel any better about this. You guys see what's going on? What's the first thing I do? Bring the 1 down. And this process does not care if the number is complex, if the number is real. The process does not care about that. So next thing I do is, multiply I times 1 is I. Add. Multiply. Yeah, I squared is negative 1. Bless you. You guys with me? Add. Bless you. Then 4i, you with me? Multiply, add, multiply, 4i times I is negative 4, and you get no remainder. Right? I desperately want you to see how this all gets connected together. So I just divided by which one of these? The first, second, third, or fourth one? The second one, because that's where positive I would come from, right? So that means that if I multiply this times this times this, I would get that. And what do I have here? This was x to the 4, so this would be... Do it. Ix squared. 4x plus 4i. Now that's something you don't see very often, is a polynomial with complex coefficients. You with me? You don't want to see that too often. In this case, it's like a middle step. If I divided this again by negative I, I would get this product, which is real. X squared plus 4. Yes?
For writing i's in the polynomial form, do you always put it in front of the x, or does it not really matter?
It doesn't really matter, but just to
Make it easy.
make it like a coefficient. Yeah. But it really doesn't matter. Yeah. But it's just so, the reason I do it is because if you saw this, your brain might look very quickly and go, oh, there's ones. Right? Well, no, it's the I at the end. Oh, shit. So that's why I always put those up front. Okay. So you will have to do this kind of thing in the homework. All right, take it all the way out, and then tell me what the zeros are. If you have a 0, if you have 3i plus 1 is a 0, what also has to be a 0? 3i minus 1 or negative 3i plus 1. One way or another, that's the same thing. It's got to be the complex conjugate. Right? Because conjugates, the complex numbers always have to show up in those pairs, those conjugate pairs. Damn, the clock's not moving faster. Let's do that. I love when I see everybody's eyes going in. Clock. Alright, let's see. So let's try one of these. Let's try a couple things out from the homework just to see what these things look like. On page 276.
We're in 3.6 now.
Oh yeah. Let's look at number. This one looks kind of freaky. Number 28. I like that. What the hell is 729? What do I mean by that? I want to try to figure out how many things are in there, because I know I have 6 x's here. Right? So maybe this is squares, maybe this is cubes. How many what's?
6 for is 3.
Good. This would be 3 to the 6th power.
Yeah, how would you say it?
Right, 729 is 81 times 9. 81 is 4 3s, 9 is 2 3s, so there's 6 3s total in there. How you guys doing? Doing a great job. So, whenever you see a problem with it, now tell me, is it squares or cubes?
What is?
Whatever you just said, you're right, because it's both. Right? So how do you tell us the squares? If everything can be cut in half, well, I can cut 6 in half. How do you tell us cubes? If everything can be cut in thirds, well, I can cut 6 in thirds. So if you can look at it either way, whenever it comes out that way, you do squares first. Because what you'll end up with in the next step normally will be a cubes thing you want to attack. If you do cubes first, your big dude is going to be freaky. It's not going to be easy to factor. So let me do squares first. How will I do squares on this? Now don't let that be difficult. It's never hard to do squares. What do you do with everything?
X cubed minus 9.
Yeah, just cut it in half. X cubed minus 3 cubed.
Plus 3 cubed.
X cubed plus 3 cubed. That's crazy. All right, so how ugly I make something if it's difference of squares, or even sum of squares now. We just throw i's on there. Easy. Let it be easy. Now I've got cubes, and we just did some cubes earlier. Each one's going to be basically the same, except the minus and the plus are going to be different, right? Let's give me a little dude here.
X minus 9.
Yeah, 1x minus 1, 3. So the other 2 x's are there. The other 2 3's are there. Middle term will be
3x.
good. Plus 3x. Please don't let cubes be difficult. They're not difficult. I can completely say that to you now. And if you think they are difficult, they're not. You're looking at them wrong. They are not difficult. So the other guy's going to do the same damn thing, except the only difference will be...
Second sign.
Yeah, the little dude's now going to be plus, and this is the cleanup dude. He's got to be... That last term is always positive. So I saw a lot of soap. You guys use a lot of soap, which is good. What do I mean? That's soap. Same, opposite, always positive. That's fine. I'm okay with that. But the more of that kind of thing you use, the less you remember why it's that way. So I never really teach too much of that. I'd rather you just kind of be able to build off of the idea of something. That'll take you a lot further. Now I'm done as far as Math 110 would say. But we are no longer in Math 110. So screw that way of thinking. Now, of course, I'm done here and here. What can I do with these two? If I want to factor it, it's sort of a trick question because the way I emphasize that. You can certainly, all day long, you could use quadratic formula on this.
3i.
That's sum of squares.
It's not going to be that. It's not going to be that easy. It's not a sum of squares. It's 3 terms. Right? And it's not going to be pretty because there are no factors of 9 that add to be 3. I don't know if you guys remember, you can never factor the big dude. And when I say that, and I know some of you guys are saying, Jeff, you just now said, we're going to factor the damn thing. See, this is what I hate with math teachers. But when I say you can't factor the big dude, I'm still talking like we're in Math 110, which is meaning I can't factor it using nice integers. I can factor it, in fact, I will factor it using irrational, possibly complex numbers. You with me? We didn't want to do that before, and I don't blame you, but now we totally can. So how would the quadratic formula look for this guy? Yeah, negative b, give or take, square root.
9.
Yeah, b, not 3 squared minus
4 times 1 times 9.
all over
2.
twice 1. I love it. Sweet. All right. So what are we going to end up with inside here? 9 minus 36, I like it, which is?
27.
Seems like, dude, you want me to go all the way there? I did my part. Leave me alone. Negative 27, right? So that means I'm going to get 2, what kind of answers?
Complex.
Complex, right? I've got a square root of a negative. What's one thing you can do with this? Yeah, simplify this a bit, right? 27 is 9 times 3. I can't do 3. But square root of 9 is 3. And for the negative, I pull out 9. That always sounds horrible. Right? And you can do the same kind of thing for the other guy. So when I factor this, I get x minus 3. Now, how the hell This, if you just wrote this, if I ask you to factor something and you write this, you are completely wrong. You have answered some question that's not even there. Right? In fact, some of you guys did that before, and right now you're like, you just did what I did. Well, I'm going to do one more step than you did. I'm just going to make it right. If I get x equals plus or minus 2, where did that come from?
X plus X minus.
X minus 2 for the positive, x plus 2 for the negative. Yeah, exactly. So if I pull that back into what factors they would have come from, then I'm right. You would have been right. So, oh God. So what I actually have negative 3 plus 3i root 3 over 2, and I have negative 3 minus 3i root 2. Not 2, 3. Those are my two answers from here, right? So one little factor is going to be x minus this guy. And the other factor is going to be x plus. Where am I going? No, I'm sorry. X minus the other guy. I'm getting a little ahead of myself. Because now you can take this negative through and make it plus, but that's what you do first. So x minus 1, x minus the other one. The same way you would have done x minus positive 2, x minus negative 2, which makes it plus. Do you guys see the connection? If you can do this work, as long as you put it back into that factored form, you're fine. I'm asking you to factor something. So I mean, you clean this up, you would take this, make that plus, make that minus, however you want to clean that up. Are you guys, this is old news. You certainly should be able to do this. The only new thing that's not really new is just throwing it in there. X minus one answer, x minus the other answer. Yeah.
Where did you get that x from? The x minus.
So I'm breaking this thing up here.
Oh, okay.
Yep. So this guy has these zeros, and how does 0 show up in factors? X minus a 0, x minus another 0. So that's all I'm doing there. X minus 1 0, x minus the other 0. Yeah.
So it's always going to be subtraction, even though it's the plus 3x for filling it in?
Yeah, because here this will go plus, the negatives will cancel. Yeah. Okay. All right. And then I have x plus 3. And you can do exactly what we just did here. You can do it for this guy here. Same exact way. Do quadratic formula for it. Finish it out at the end. Oh yes. This is pre-calculus. Pre-calculus is this. It's a lot of graphing and it's a lot of intense algebra. That's really all this is. It's just algebra. Yeah.
So if you factor or do the quadratic formula for the second, would you get basically the same answer except it's positive 3?
Well, the only thing that would change is you would get, instead of having a negative 3 here, you would have a positive 3. Because the only other place that b shows up is a b squared, and that's 9 no matter what. If you have a positive or negative 3, you with me? So I like the way you're thinking. How would this actually change? Instead of a negative 3, you'd have a positive 3, because now what's negative b? Negative 3 is positive 3. So it'd be exactly the same look, except this would be positive 3, that'd be positive 3. Okay.
So if we had something like that on the test, would you mark us down if we didn't do it the second time?
Of course. Yeah. Alright. You guys good?
Yeah.
I'm just doing that just to save time. We could just do the whole thing again, but like you said, it's just going to be a 3 there. Not a big deal. Okay. That looks exciting. That's the kind of thing they're going to want from you. And here's the thing that we just did. Look at number 37. They want you to write a polynomial that does what they say it does here. It tells me q has degree 3, and the zeros are 3, 2i, and negative 2i. So how would you put together that polynomial. The 0 of 3 would have come from what factor? Exactly. Don't let that be difficult. If I see x minus 7, I know the answer is 7. If I see the answer is 3, I know it must have come from x minus 3. It's just as easy going each way. So I know it has a 0 of 3, which means it must add a factor of x minus 3. It has a factor of 2i, 0 2i, so it must add a factor of x minus 2i. And it has a factor of negative 2i, so it must add a factor of x minus negative 2i, which is x plus 2i. See, it's always minus. It might become plus on the next step, because it might be minus and negative. Not a big deal. But it does always start off as x minus whatever the 0 is. In this case, it just becomes x plus 2i. See, did they say? Oh, I like it. And they actually do say, just leave it like this. Multiply that bad thing out. If you have any conjugate stuff in there, that's the easy part to start with. Kill the i's. And it's difference of squares. It always has to be a difference of squares idea. That's what the complex conjugate's all about. So what do you get when you multiply these two things out?
X squared plus 4.
The middle term cancels? Yeah, minus 4i squared, which is plus 4. I love it. And then just FOIL that out and you're done. So if you do that multiplication step, and the last step you still have i's running around, you have made a mistake. All the i's have to cancel. It better come out with real coefficients. They say that. Blah, blah, blah. Integer coefficients, even better. So what if I said, I don't know, Jeff. What if I said, let's see if they say this anywhere. Nah, sort of. What if I said p of x has degree 5, and the zeros are 2 and I. Now what kind of doesn't jive there? Not of zeros, but I know right off the bat, if it has a 0 of I, it's got to have a 0 of negative I. So right off the bat, I have one more. Is that enough?
No.
So I bet you anything that the 2 has to be repeated how many times?
3 times.
3 times. To make a total of 5. So right now, if I just wrote it the way it is, I'd have x minus 2, x minus I, and that's down by 2 pieces, right? Because it's supposed to be a 5th degree.
So you just cube the x minus 2.
Yeah, exactly. You could, yeah, that's even better. So you can have x minus 2, so just cube that bad boy, so you're good. It didn't say anything about multiplicity. It just said it has a 0 of 2. And we're just going, oh, it's repeated twice.
So can you do any time that you're given not enough zeros and there's none that like
You can just make some more a multiplicity bigger than 1.
okay.
Another way to do the same thing, there's one of those. If I would make each of these multiplicity 2, is that a 5th degree? This would together be what? X squared, x squared. This is a 4th degree times x. 5th degree, sweet.
So those would both work?
Either one of these. So according to these instructions, there's 2 basic answers that I would accept.
But those are different. Those are different.
Different. There's entirely different polynomials, but they're both degree 5 with zeros of these. Just they have different multiplicities of those zeros.
Would you expect both answers?
No. But if you put them both, what the hell? It'll make me go, aw. But either one is fine, yeah. You guys with me? This actually goes a little further than the book does. The book doesn't do that thing to you. I enjoy doing that kind of thing, so that's good.
Wait, the book doesn't give us.
What the book does do is it gives you that. Then you fill it in, but it would say 3rd degree. It wouldn't play with the multiplicities, but that's not that hard, is it? If you write down what you get from these 3 and you go, shit, I need 5, just give somebody more multiplicity.
So
let them show up.
Test question?
Oh yeah, this is completely a test question.
So would it be wrong if you put a cube like on the x plus I?
Definitely, for 2 reasons. Well, maybe just one reason. I don't know which way you're thinking, but if you made that 1 and that 3,
You wouldn't have your pairs.
you wouldn't have the conjugate pairs. right? So that's why if there's one of each, or there's two of each, or there's three of each, they have to be the exact same amount of each, so they have their conjugate pairs. Is that cool? All right, good. That was, for you guys, that was a huge reaction right there. I like that. Some of you actually had your head going up and down. I'll stop joking here for a few minutes.
We do some practice problems with that, like harder ones.
That's harder than the book.
Okay.
That's the hardest you would see from me. And it's only difficult because I left the information out about how to make it a fifth degree with only 3 zeros. So all the book does that's bad is they give you I and you just make a negative on it. Not a big deal. So this is the furthest I would go with that kind of question. But you can imagine I could say as a 0, -3 minus I, 2 and 0, and it's degree 7. Well, if it's got this guy, it has to also have -3 plus I, and it's supposed to be degree 7. This would only be degree 4 so far, so you make the multiplicity so that it becomes 7. It's really the same idea as that. Just a little bit more gross here to work with. Blah, 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 blah. Okay. So that's section 3.6. Really nothing new compared to 3.4, except they have complex answers possible. Okay, so I want to do a little bit. Sweet, I got plenty of time. I want to do a preview of the next section if there's no questions off of this one. Or maybe I'll do, let me give you one example here. This will be a review of synthetic, making your list of possible roots, all that kind of stuff, right? It's not a bad idea. Let's do that. So do everything I just said for this guy here. Let me do a couple things with you. What would Descartes, go ahead and write that down, but then think about what would Descartes say about positive real roots. Almost, except you used
there has to be one.
has to be one. Exactly. There can only be one. Because how many changes of sign are there here? One. So positive real roots. One, because then if you go down by 2, that's negative, and that's free. How do I look at negative real roots? What do I have to look at to figure that out?
The degree minus the number of positive roots.
No, gotta be careful. I mean, we'll find out what happens here, but sometimes it won't come out to be that, because then there might be definitely complex roots for something. You see what I'm saying?
Turn all the x's negative.
Yeah, so if I do p of negative x, what do I get? Which ones don't change sign if I do this? The ones that are to even power, right? Because the even powers will kill the negatives. Are you guys with me?
Yes.
You guys scare me sometimes. So if I do this, 4th power kills the negative. So it makes this whole thing very quick. All the even powers stay the same. All the odd powers switch. How many sign changes? 1, 2, 3. I like this.
So they're all real. There's no imaginary solutions to that.
Be careful. So what does it say then? There could be 3 or 1, because there might be 2 complex.
Wait, why do you know there could be 2 complex?
So I know there's got to be 4 answers.
Yeah.
Descartes classifies them for me. Sometimes he's very specific and sometimes doesn't do much. But he's definitely said there's definitely got to be 1 positive real root.
No.
Which means there could be, the other 3 roots could be negative real roots.
No.
Or 2 of those, because they have to show up in pairs, could be complex, meaning one of them could be negative. So I'm guaranteed 2 real roots.
Okay.
At least.
And you just have to start.
You just have to start breaking it up.
Okay.
That's right. So sometimes Descartes helps me cut my list down, and sometimes he doesn't do shit for me. In this case, I can't really cut my list down, right? Because it could be negative or positive. What are my possible roots? Rational roots. Where did I get that from?
The negative 18.
The 18. So what are those possible roots?
Plus or minus 1.
You know, all the factors of 18?
18.
Yeah, 3 times 6 is 18, 2 times
9.
9, and 1 times 18. Cool. Alright, so now you guys try to finish that up. Try to find the roots. At least there's not a possibility for fractional roots here. Trying to find the silver lining. If you're a gambling person, usually not. Which one is there a slightly higher probability that there would be answers there?
Negative.
Negative. So I start to divide by -1, -2, whatever. You might want to try to divide by like 6 or something. Maybe it'll be a upper or lower bound, 6 or -6.
-2 works.
There you go. So you just give something away. This is our polynomial, right? Look, notice if I divide by 3. Oh, what's that? That's 198. What's
Positive, that's upper bound.
beautiful, right? So I know that 3 it's not an answer, damn, but it is an upper bound. Which means I can throw out 3, 6, 9, 18, those will not work. You guys this is just to remind you what bounds are all about. If you happen to notice that while you're doing the work, that's awesome. It's a quick little, I can throw out anything above it. If it's lower bound, I can throw out anything below it. But I think you just said 2 works. So let's see, 1, 2, 3, 6. Is it 2 or negative 2?
No, it's 2, but it's negative 2 when it's,
All right.
yeah.
Negative 2, so because that's going to go a little crazy. In fact, 2 might be an upper bound too here, it looks like. So yeah, if we do negative 2, what do we get?
2 comes down.
Well, negative 2, negative 1, 2, 9, negative 18, negative 9, 18, 0. The gas.
1 also works.
And I want you to notice something. If I just say, I'm giving this away. What factor did this come from? X plus 2. And what's left here? It was x to the 4th, so now this is x cubed. Can you factor this?
Yes.
Yes, so that's why you want to collect what you've got so far, so you don't go crazy with synthetic. But synthetic's relatively easy. It's actually either way you do it, but this is just grouping, right? And that'll go somewhere pretty quickly. You guys with me? No? Yes? I mean, I could keep doing synthetic on this, and I'll have some more stuff that works, of course. But I also have just something that's grouping. So it'll be x plus 2. Let's see. X squared plus x squared comes out of there, and a 9 comes out of there, and I will be left with x minus 1. I skipped a few steps there for the grouping. So you said 1 works, right? So there's that x minus 1 piece that goes with that. So it looks like, what did Descartes say again? 1 real root, 1 positive, so there's 1 positive, 1 negative, or 3. So I got 1 negative root, and the other 2 that could have been negative actually end up being complex. Right? So that's why we say 3 or 1. We always go down by 2 because it might have 2 complex for that pair. So then, to finish this out, it'll be x plus 2, x plus 3i, x minus 3i. So all my zeros would be negative 2, negative 3i, plus 3i, plus 1. That would be a list of your zeros. Problem done. Right? So I have any problem with stepping out of synthetic division at any point that you end up with something that's factorable. Why not? Because synthetic's pretty easy. You can keep going with synthetic if you want to. Maybe. Okay. So a little preview of 3.7, and we'll get out of here just a little bit early. Let's see. So this is the kind of function we're talking about in section 3.7. It's not a new function that we're going to talk about, but what's new for most of us will be graphing these things. And you could probably expect that when you start dividing polynomials, you get some weird things happen. Right? And the most basic example of this really would be 1 over x. Does anybody have any idea what that graph looks like? No, sir. Okay. So, think about it for a second. What's 1 divided by 2?
1/2.
What's 1 divided by 1? What's 1 divided by 1/2? 2. So you get that kind of thing going on. Make that real big, you're fine. And then the negative kind of stuff happens the same way. So that's what that looks like. What the hell is going on right here? And there. Look at you with those words. What does that mean?
The limit.
There's no zero be.
The limit exists. You gotta be careful.
Yeah. It did.
If you want to bring some of that limit stuff to me, bring it. What's the word that goes with this?
It's approaching 0.
Asymptote. Look at you. Yeah. So that means it's approaching 0. So as x goes to infinity, f of x goes to 0. Now I'm going to go one step beyond that and go with what you just said over there. Especially for those of you who are going to go into calculus. One of the first things you're going to be doing is working with this kind of thing. The limit as x gets really freaking big of the function is 0. So limits allow us to go places we actually can't go. The limit says, can you get to infinity? If you think you're there, take one more step. Oh shit. So you're not there. Right? So you cannot get to infinity, but the limit says, let's pretend like you can. If you could get to infinity, then the function would be 0. That's what that's saying. Right? You guys with me? That's what an asymptote really is the limit as x goes to something, is some number. That means it's got to approach that. Right? It's got to get really close to that number, but it never quite gets there. That's what an asymptote is all about. So here I see something freaky happening here and there. The limit as x goes to 0 from above is as x goes to 0. See, as all my inputs go to 0, what are my outputs doing? Getting really freaking big, right? Which makes sense. 1 divided by 1/10 is 10. 1 divided by 1/100th is 100. The smaller my bottom is getting, of course, when I divide by small, I get big. So divide by stupid small, I get stupid big. And that's what that means. That's a vertical asymptote here. This one would be a vertical. I like the way I really emphasize it. Yes, Jeff, it's vertical. Yeah, that's a vertical asymptote. And this is a, incredibly enough, horizontal asymptote. That's so. We'll also have slant asymptotes. Of course we will. Why not? Now the other side, as x goes to 0 from below, what's the function doing? Going to negative infinity. This notation here you will not see in the book. I just want to get you guys used to what that notation means, so that if you are going into calculus, it won't freak you out when you first see it. And if you're not going into calculus, I don't care. You can look at it this way. The book uses this. That's what this means. As x gets really big, the function gets really small. It goes to 0. Okay, cool. So what we're going to do in section 3.7 is we're going to look at a function like this and determine where are its vertical asymptotes, where are its horizontal asymptotes. They're not going to be the same as that necessarily. Right? This has got a lot of weird crap going on. They've moved around. Maybe they've shifted. They've translated. In fact, why is there a vertical asymptote at 0 here? Because you can't divide at 0. So it seems like vertical asymptotes, there are these walls that you set up that your function cannot go across. So what to do when it sees is, oh shit, pull up. Like that. I've got these weird movies in my head. It's a trap. Alright, I like that. 3 people got that. Cool. So, what x values are you not allowed to use in that function? What would you do to see that? Yeah, where are you seeing that? What are you doing?
Factoring it.
Factoring the bottom, so you can see what it's made of. Right? So the bottom factors like how?
X minus 2,
X minus 2, x minus 3, 11. So x cannot be
2 or 3.
2 or 3. So if I were going to graph this function, I know that at 2 and 3, there are walls set up. My function is going, yay, oh shit. It's got to come up against that wall, right? Or down against that wall. Yeah, maybe. Yes, sir.
Is it possible for them to just skip it? Like, because I know sometimes
Yes.
holes in graphs.
We're going to get there. And the way that would work, let me see. The last thing I wanted to do with you guys today is do this for me. I'm going to connect it with what you just said. Let me see if you guys can handle this. All right. In your calculator, I want you to let x equal 0.01. No, we need to be careful. Let x equal 2.01. Because I want to use this function here. So what number am I getting really, really close to? 2. I'm just not right on 2. Because can I plug a 2 in here?
Yeah.
No.
You can do 2.2.
But I want to see what's the limit as x goes to 2. So what am I going to do in my calculator? I'm going to put a number in that's really freaking close to 2 to see what it does. Let me see if you guys can do this. So in your calculator, you want to put in there exactly this, 2.01 minus 1, that's the top, divided by 2.01 squared. Oh, where'd it go? Minus 5 times 2.01 plus 6. So that's exactly what you want to put in your calculator to do this. I'm using it without this, because otherwise I don't want to use all these freaking parentheses. Let me just use this form of it.
Negative 102.02 bar.
Let me let everybody else get there too. I see a lot of other people playing along with this. Sounds about right. So who else got an answer that you're willing to share? Cool. So that's what you got, right? Negative 102 point blah blah blah. So that's getting pretty big negative. So I'll bet you at this asymptote, at this vertical asymptote, as I get close to 2 from above, I'm getting close to 2 up there. I didn't put 1.99 in it. I put 2.01. So it's going to get really big negative. So it's going to go like this. As you get closer to 2, it's got to get close to that wall. It's got to go down to negative infinity at 2. That's the connection between what's really going on concretely and what does that translate to picture-wise. Now I'm trying not to do too much because I don't know what it does past here. But I know it would do that. I could do the same thing. I could put 2.99 in there and investigate what does it do when it gets close to 3. I might have to put 2.99, 2.999, get really close. It depends. That's really the first 2 weeks of calculus is you're doing a lot of that kind of thing. Get really close to this number. Now get really close to that number. What's going on? Okay, maybe. So that's vertical asymptotes really are just what x values are not in the domain. So like you said, here, when I get really close to 2, what's the top? It's basically getting close to 1. But the bottom is getting really small. Are you with me? So 1 divided by really small is really big. It just happens to be getting really big negative. So your question was, does it always have to do this kind of thing at a vertical asymptote? No. It just can't exist there. But if I had one like this, if I had made it this instead, now this gets really, really small when you get close to 2, but this gets just as small, doesn't it? So they would effectively cancel each other out. It doesn't let it go to infinity. This guy is lockstep with this guy. The top gets just as small as the bottom does. So it's small divided by small is some number, I don't know. So that's this very specific case. We'll talk about that later, but that's how that can happen, where you don't have to have a slam up against it. You could actually have an open circle there. It just can't be there. I still can't plug 2 in. Right? But in some sense, they cancel each other out. Okay. All right. So that's enough for right now. Next time, we'll get into horizontal asymptotes and graphing these things. I have a handout, but I'm not going to give it to you yet. We haven't talked about enough of this yet. Oh, real quick. Lewis? Soda? Janice? She's still here? Kristen? Sawyer?
Right yonder. That's correction we're going to do Wednesday.
Gio? Yeah.
Test corrections are due Wednesday.
Next Wednesday, yeah. The day of the next test.
Okay.
Yep. Gio, Jameson? Nope.
I have a question. So, if